This is my research on automated histogram bins for weighted samples. So first, let's start on what histograms are. They're a type of data visualization, and they utilize something called bins. And bins are ranges, like say like 1 to 3 or 10 to 12. And if a sample falls into those bins, then it increments, like you can see at this graph here. Like all of these bins represent like hundreds or maybe even thousands of samples. Like here's a histogram of 1,000 samples. And why these are so important is that they show the underlying distribution of how the samples are. Like, for example, this is a normalized distribution, which means that it has this bell curve, as you can see in the blue line. And this orange histogram represents that bell curve. And you wouldn't really be able to tell this if the histogram wasn't there. Now, in coding, you can usually compute histograms with like one line of code, but that line of code goes through many different steps, so I'm going to run through them. First, you have to find the range of the samples, which is simply just subtracting the maximum sample from the minimum sample. And then you need a number of bins. That is already defined when you ask the code to create your histogram for you. And then to get your bin widths, it divides the sample range by the number of bins that you ask for. And that will basically tell you how wide your ranges for your bin widths are going to be. And then you determine the edges of your bins. As I mentioned before, they're just ranges of numbers. And then the computer goes through your sample list, and then it sees which bin your sample falls into, and then it creates your histogram. So this is the same histogram diagram as before, but it's just a little bit more detailed. So as you can see, this is what a bin width is. And then this is the whole range of all the samples. Now, the number of bins that you use for your histogram is actually really important because the whole purpose of a histogram is to see a good representation of the data distribution. So if you use too many bins, for example, then you get something like the top graph here. And as you can see, this is barely readable because there's way too many bins, which makes the histogram appear jagged, and there's way too much detail. And you're going to have a hard time analyzing this data. On the other hand, if you use too few bins, they end up looking really large like this. And then you're just grouping together a bunch of data that probably shouldn't be grouped together. As you can see by the width of these bins, it's really, really long ranges. And this also won't give you a good idea of the data distribution either. So the main goal with automatic bins is basically to get the optimal number of bins. So your graph doesn't look like this or like this. It looks like a perfect medium. So there are many ways to find an optimal number of bins for unweighted data. And unweighted data is basically data where each data point is treated the same. We'll go into weighted data later. But one way to find the optimal number of bins with unweighted data is the Freeman-Diaconis rule. And this rule is used to determine bin width, and with that bin width, you can find the optimal number of bins. So to the right, you'll see the equation of it here. I'll break it down for you. So first, the IQR, which is the interquartile range. That is when you divide a data set in half, and then you take the median of the first half and the median of the second half, and you subtract those. If you have a smaller interquartile range, when you use this equation, then you're going to get a smaller number of bins. And if you use a larger interquartile range, you'll get a larger number of bins. And the interquartile range gives you a better idea than using the full range because it's more focused on the middle concentration, which for normalized data, like I said, it has that bell curve. So the middle is the most important. So that's why using the interquartile range is really good. And then the second main important is this n here, if you can look at the equation. And the n stands for the number of samples in the data set. And if you use more samples, then you'll get smaller bins, less samples, larger bins. Now, I mentioned before weighted samples. Weighted samples are when regular samples have added coefficients to them. And these coefficients make the data either less or more important in the calculation. For example, if you're trying to find the average height of people in North America, let's say, you get data from Mexico, Canada, the US, etc. You would put more emphasis on the data from the US because there's more people in the US. So you would make the US data more weighted to reflect that. And the really important thing about making sure you graph weighted data with their weights included is because you can end up with two completely different graphs. If you look at the graph here, the blue is data that is come from a uniform distribution, which means that it's all kind of around the same number, like there's no bell curve with uniform data. And as you can see, it looks pretty flat like this. But this uniform data has weights that are in the normal bell curve distribution. So if you don't graph the samples with the weights, they look like the blue. But if you graph them with the weights, it looks like the orange. And the orange is what you want because this is what the data actually looks like. So if you account for the weights, then you get to see the true distribution of the data. Now, to make the Friedman-Diaconis rule work for weighted data, because as mentioned before, it only works for unweighted data, you have to change how the interquartile range and the number of samples work. So first you need to find a weighted version of the interquartile range. And you do that by finding the interquartile range of the weights rather than the actual samples themselves. And then instead of using the regular number of samples like we did before, we need to use an effective number of samples. An effective number of samples is basically the same thing as the number of samples, except that it's generally smaller, and that's because it's not taking into account most of the outliers that you'll find in a regular data set. So it's much more confined and cleaner, which helps with the optimization of the number of bins. So here is a graph of using this weighted version of the Friedman-Diaconis rule. As you can see, the number of bins here, it's not too many and it's not too few, and you can really tell the distribution of the data, which is why it's really nice to optimize data like this. So just a quick summary of what I've talked about. Histograms are a type of data visualization that groups similar values using bins. With your interquartile range and the number of samples that you have, you can use the Friedman-Diaconis rule to compute an optimal bin width and then compute an optimal number of bins from the data to make it look much more cleaner overall, and you can analyze the distribution a lot better. Weighted samples are samples with coefficients to where you can make them more important or less important in the data distribution, so you can get the perfect way to analyze what you're trying to. And then what my research was basically was taking the Friedman-Diaconis rule and a few other rules, but I just did the Friedman-Diaconis one for simplicity, and taking their unweighted versions and creating them to work with weighted data. And this version with the Friedman-Diaconis rule that I created through my research is actually in a Python library now, which is really nice. And I'd also like to credit my mentor, Lucas Hergen, who was a postdoc at the University of British Columbia, who helped me a lot because I had no experience with any of this before the research. And now I feel like, well, I'm not like extremely knowledgeable, but I definitely have a good understanding of it now. And that's about it.